Hello, this is Miss Meadows, and today we're going to look at metric conversions and how to use the metric system to convert between units using what we call dimensional analysis. The metric system is based on the value of 10, and it allows us to quickly convert basic units of measurement into more easily used numbers. The metric system is also known as the International System of Units, or the SI system. The SI comes from the French term Système International. The organization of the system falls into two parts: the name of the unit, which represents what kind of measurement you are making, and the prefix of the unit, which represents the size or magnitude of the measurement. For example, I can use a ruler to measure centimeters. Meters is the measurement of length, while centi is the prefix meaning 1/100th. So a centimeter is 1/100th of a meter. Measurements in metric that are common to chemistry. So these are the ones that we are going to see most often in this class. We have two groups shown here. On the left, we have direct measurements. Direct measurements are things like meters. Meters are a measure of length or distance, and we can use a ruler or a meter stick to directly measure that unit. A gram is one we will use a lot in this class, and grams measure mass, or how much matter or particles you have present. And we use a balance, which is typically an electronic balance, to find that. We also will use liters. Liters are a volume or amount of space that matter occupies. Typically, if we're measuring liquids, we will use a graduated cylinder or a flask to measure volume. But if you have a regular shaped object, like a cube or rectangle, we can also use a ruler because the volume is the same as distance cubed. So we could take the length times the width times the height and get our volume that way. Then we have on the right side calculated values. So there's no device to directly measure these, but they can be calculated based on other measurements. They are still considered metric units though, so we can still convert these between the metric units using prefixes. So the mole is a very important unit for chemistry, and it represents the number of particles. So if we were to count how many particles there are. It cannot be directly measured. So there's no instrument that's going to count our number of particles. So we measure things like grams and then convert it into moles. And then our last one is joules. This is the amount of energy in something. Again, we can't directly measure it. We can measure other things and then calculate energy using an equation. Metric prefixes. So why do we need prefixes? Let's look at an example to help us see why they're so important. So the apple shown on the balance below is recorded or has a recorded mass of 90.0 grams. So that's the mass of our apple. If we were to put 10 of those same exact apples on that balance, we would show a mass of 900 grams, so 10 times bigger. If we were to put 100 of that same apple, we would see a mass of 9,000 grams. So our mass just gets bigger. And again, if we were to put 1,000 apples, we would see a mass of 90,000 grams. So we can see as we add more apples, the numbers start to get very large and harder to report. It would be very easy to forget a zero and cause our data to be flawed. So as we get bigger and bigger measurements, or even smaller and smaller measurements, our numbers get a little harder to deal with all of these zeros. But the metric system is here to help deal with this. The metric system uses prefixes to show size without changing the number. So we're going to change the size of the unit we're using, but not the number we're actually recording. So let's see how that works. A prefix is the name of a metric unit, or in the name of a metric unit, describes how large that unit actually is. So let's see how prefixes can help with our data from our apple example. So in this table, I've taken the data we have from the previous slide on our number of apples and the mass of the apples, and those are in the first two columns. Let's take a look at the first row across. So if we took that one apple, we saw it measured a mass of 90.0 grams and grams are our base unit. So that's kind of like the basic unit. One apple is our basic measurement. So that's still just 90 grams. The abbreviation we're using is G for it. That's what represents grams, and it has a value of just 1. Now, if we went to the next line and we have 10 apples, the mass of 10 apples was 900 grams. So it's a bigger number. Well, if we didn't want to change that number, what we could do instead is add a metric prefix. So in the next column, it says 90.0 decagrams. So deca is a prefix added to gram to show us the size of that gram. So in the next column, we can see its abbreviation is DA for deca, G for gram. And then the value of it is times 10. So what deca means is that it's 10 times the amount of a normal gram. So if we have 90 decagrams, we have 90 times 10 grams. It's really what we're reading there. So instead of actually multiplying the number out, we're just changing what the unit tells us, which is a little easier. All right, let's look at the next one. We've got 100 apples, so 9,000 grams. So instead of putting 9,000 grams, we could use a prefix that means times 100 instead. So 90 hectograms, or Hg, is the same as 9,000 grams. Hecto means times 100. And our last one that you might be more familiar with is in terms of prefixes. If we had 1,000 of our apples, it weighs 90,000 grams. We have a lot of zeros there, easy to drop one and mess up our number. So instead of doing that, we can put 90 kilograms, or kg, and that means the same as 90,000 grams, because kilo means times 1,000. It's 1,000 times bigger than a gram. So when, say, large amounts of product, like somebody selling corn grain or flour or, big bulk items like that, they don't want to measure in grams because they're going to have these huge numbers. Instead, they can do it in kilos or kilograms and cut their number down, but still represent the same amount of substance by putting that prefix on it. So we can see that using the prefix, the number stays manageable, and the prefix just tells us how much bigger the actual measurement is. So what if the numbers are smaller, though? Does this still work? So we're going to take our apple and look at it in a little different way. So prefixes can also help with very small numbers. So let's imagine our apple, and we're going to start cutting our apple into smaller and smaller pieces, okay? They're always going to be equal pieces. So let's take a look just at the first line across the top. It says the number of apples, we got 1 apple. The mass of that apple is 90 grams still. And we're not going to cut it into any pieces. We're going to keep it whole. So the mass of all the pieces together, it's just one piece, is 90 grams. And if we were to go to after that big bold line, kind of focusing on one piece at a time. So the mass of one piece, since it's still 1 apple, still 90 grams. Metric prefix doesn't need 1, and its value is 1. So that's kind of our baseline, base unit. Now, if we look at the next line, we've still got our 1 apple. It has a mass of 90 grams. But what if we cut it into 10 equal pieces? If we have all of those pieces together, in that fourth column, it says the mass of all the pieces is still 90 grams, because it's still all 1 apple. But if we were to take one of those pieces and measure its mass, it would be 1/10 of that, right? It'd only be 9 grams for that one little piece. So instead of saying 9 grams, what we could do is add a prefix. So in the next column, the metric prefix for the mass is 90 So we're keeping that number, 90 decigrams. So deci is the prefix that means 1/10. So we're dealing with 1/10 of our apple. So we have 1/10 of the grams, which kind of makes sense, right? So we have 90.0 decigrams. So deci means 1/10. If we were to keep going, our next line, that third one down, says if we had our one apple, weighs 90 grams. If we were to cut it into 100 equal pieces, so we're getting small apple pieces now, all the pieces together would still be 90 grams. But if we just took one of them, it would weigh only 0.9 grams. We're getting much smaller here. Well, if we didn't want to change that number, we want to keep the number the same, we can use a metric prefix, and one of those pieces would be 90 centigrams, because centi means 1/100th, just like cents in a dollar, right? We have 100 cents or pennies in a dollar. So centi means 1/100th. And the last example down here is we took our one apple, weighs 90 grams, but we were to split it and cut it into 1,000 equal pieces, which seems crazy to me. I don't even know that we could cut that, but imagine we did. The whole thing together, all the pieces would be 90 grams, but if we took out one of them, it would only weigh 0.09 grams. Pretty small piece of apple. Well, again, if we didn't want to change the number, we can change the prefix, because we start getting these small decimal numbers and it's easier to drop a zero and mess up our value. So instead, we can measure 90 milligrams. Milli is the prefix that means 1/1000th. So that little piece of apple, it weighs 1/1000th of the whole apple, because we cut it into 1,000 equal pieces. So that's how this kind of works. We're taking that unit, we're breaking it up into smaller pieces. Those pieces, if we kept them all together, would still weigh the same mass. But if we separate out one of them, it's going to be 1/10th or 100th or 1,000th of the mass of the whole thing. Okay. So our prefixes and our base units. The chart you see on the right here is all of the metric prefixes. This is what we've got. So because we have metric prefixes, you can use the same measurement, like grams, for very large and very small values. So if we wanted to measure the mass of, all the corn produced in the United States, we could use a metric unit of mass of grams, but we might put a large prefix on it because we're measuring so much. Or we can measure the mass of something like an atom, and because they're so tiny, we need a metric prefix way down towards the bottom because it's going to have such a small mass. And we don't want to have it in grams, or we'd have all these decimal places. So it's really nice to be able to say, okay, grams measure mass, and then we're just going to put the appropriate prefix on it to show how big we're measuring. So we're going to use all of our measurements like grams, liters, joules, and stuff. Those are our base units. And we're going to add any of these prefixes here. So this is all of them. You can see it goes from yada at the top, which means a septillion of something, all the way down to yocto at the bottom, which means 1/septillionth of something. So teeny tiny piece, which are just crazy big numbers and crazy small numbers. But there are some that we're going to use more often, and those are highlighted in yellow. So let's start at the top one in yellow. We've got kilo, one we're going to use a lot, especially in kilojoules. That's a very common one we use kilo for. So its symbol is a lowercase k. It means 1,000 times bigger. So a kilogram is 1,000 times bigger than a gram. And its exponent form is 10 to the third. And some of those are just easier to see as exponents for some of us. The next one down that we have highlighted says base. That's just where our base unit is. So that's our grams, our liters, our joules, meters, all of that. The symbol is really just whatever symbol is, like G for grams, L for liters. It means 1, so it's the base, and that's kind of where we start. The next one down is centi. We might see this with centimeters. That's the most common one we might see it with. And its symbol is a lowercase c. It means 1/100th. So it would take 100 centimeters to equal the base unit. Okay, so that's kind of how we interpret that middle part, that multiplier. So 1 centi, like meter, represents 1/100th of a meter, but it takes 100 of them, if we add them together, to equal 1 meter. The next one down is milli. We use that a lot, milligrams, milliliters, those sort of things. So its symbol is M. So if we have millimeters, we have mm. And it is 1/1000th. So it would take 1,000 millimeters or milliliters to equal the base unit. And then the last one that's highlighted, we will run into in a particular unit on waves and light and dealing with electrons and things like that. So it's nano, and we use it with nanometers to measure the length of a wave of light. And its symbol is lowercase n. And it represents 1/1 billionth of the base unit. So it would take 1 billion nanograms to equal 1 gram. Okay. Really quick, going back up to kilo. So when it says kilos multiplier is 1,000, it means that it takes 1,000 of the base unit to equal a kilo. Okay. So when you're looking at that multiplier, it's always the ones below base are how many of that it takes to equal the base unit. So like centi is 100 centi to equal a base, or milli is 1,000 milli to equal the base. And then when you go from base to kilo, it takes 1,000 of the base to equal the kilo. So it kind of might help you. And these are in order. So top to bottom, we're going biggest to smallest here. So that's going to be important so we know which ones are bigger than others. Okay. The other thing down at the bottom is next to our chart here. I have some labels, and it's just to give you a range of things to show you when these might be useful. So nano, if we're measuring like the diameter or the radius of our atom, we're going to be in a nanometer range. So pretty small atoms are pretty small here. We're looking at 1 billionth of a meter. So it's like taking a meter stick and breaking it into 1 billion equal pieces. That's how small atoms are. Now within our atom, we have our nucleus. And the nucleus's size, its diameter, would be in the femto range. So that's a quadrillionth of a meter, which is just crazy tiny. And even smaller than that is our electron size. So if we looked at the diameter of an electron itself, it would be in the atto range, which is a quintillionth of a meter. So very, very, very small. So we do need these. It seems like they're so tiny, but we do need them to measure certain things like this. All right, now we're going to look at converting from the base unit into something with a prefix, a metric prefix. So given a value in a base unit, we can convert it to another unit of the same measurement. So if it's in grams, we can go to something with a prefix in grams. And we do this by multiplying or dividing by multiples of 10. So we saw on the previous slide that everything is based on 10. We're looking at tens, hundreds, thousands, millions, billions. It's all based on 10. So everything we multiply and divide by here is based on tens or multiples of 10. So we're going to look at each of these examples separately. So our example says, what is 783 meters in kilometers? And then in centimeters. So that's two separate questions we're going to do. So when we set up a metric conversion, we're going to use what we call the railroad track method. Hopefully you remember this from your honors chem class. And basically it's just a method of setting up our values and showing how the units change. It's called dimensional analysis. This is really important in chemistry, and we use it in all kinds of different conversions. So understanding it here will make other conversions much easier. And yes, you do need to show work and be able to do this method. So 783 meters is our given amount. That's what we have, and we want to change it first to kilometers. So in our little T-chart in our railroad track, we're always going to start by putting our given amount, 783 m for meters, in the top left corner. It's just our starting point. And then what we want to do next is get the meters, because we don't want those anymore. We want them to cancel. So we're going to place m in the bottom right corner so that those are one's on top, one's on bottom, and that will allow them to cancel out with each other. And then on the top above that, we want the unit we're trying to change to. So in this example, we're trying to change to kilometers. So we're going to put km for kilometers. And then we need to look at just this right side of our little T-chart right here. So we've got km over m, kilometers and meters. We want to know what the relationship is between kilometers and meters. So to decide that, the first thing that we do is decide which one's bigger. So thinking back to that chart we had, we want to go with the one towards the top. So kilo is bigger than our base unit, meter. So whichever one's bigger, we're going to put a 1 next to. Then we're going to think about the relationship. So a kilo means 1,000 times bigger. So if the top says 1,000 meters, essentially, because 1 kilometer means 1,000 meters, we want the bottom to also show that. So 1 kilometer is equal to 1,000 meters. So we think about the relationship there and think about which one's bigger. We put a 1 next to it, and then how many of the smaller one does it take to equal that 1? Next, we want to do our math. So the way these are set up is so that it's essentially a math problem. It's setting up fractions and these what we call conversion factors. But it does it in a really clean way so that all we have to do is multiply our numbers on the top and divide our numbers by any number that appears on the bottom. So if we were to read this, I would take 783, multiply by 1, then divide by 1,000. Well, when we multiply by 1, it doesn't change our number. So we have 783, we're dividing it by 1,000. You can do that in your calculator. If you're comfortable doing those calculations in your head, you can do that too. So a kind of simple way when you're dividing by multiples of 10, like 1,000 is a multiple of 10. Really, when you're dividing by those, you're moving the decimal from the number to the left, however many zeros appear there. So we have 3 zeros in 1,000. So really, we're moving our decimal to the left 3 places. 1, 2, 3, because we're dividing, we're making the number smaller. So our value should be 0.783. And then we've canceled out our meters because they're on the top and bottom, and we're left with kilometers. So we get 0.783 kilometers. So if you have 783 meters, it's equal to 0.783 kilometers because kilo represents that 1,000. It's a bigger unit. So our number should get smaller. All right, we're going to do a similar problem, but now we're going to look at centimeters. So we're going to convert our same 783 meters, but this time into centimeters. So we're going to go ahead and set up our T-chart again. We're going to have our given 783 meters in the top left corner. And just like the previous one, we want to go ahead and put meters on the bottom to make sure that they will cancel. So we design it in the way to actually make them cancel. And then we put the unit we want on the top, which in this case is centimeters. So C for centi, M for meters. And it's always good to leave you notice I put my units towards the right side of my little T-chart there, way over on the right, so I've got plenty of space to write my numbers. Now, we're going to focus in on that right side and we're going to decide our relationship. So first thing we want to decide is which one of those two things is bigger. Is a centimeter bigger or a meter bigger? Now you can think back to our table with all the prefixes in it and think about which one's bigger, the centi or where the base unit was. Well, the base unit is higher on that list, so that's our meter, and that would be the bigger one. So the bigger one gets the 1. Now we want to think, how many centimeters do we need to make a meter? So centi represents 1/100th, okay? So it's 100 times smaller than a meter. So it's going to take 100 centimeters to equal 1 meter. Now that we've filled in our numbers, this is when we can do our math. So we're going to multiply across the top, divide on the bottom. So 783 times 100 divided by 1. Now again, we can put it in a calculator, or you can also think of moving, since we're multiplying, we want to move the decimal place to the right, and we want to do it 2 times, so we have 2 zeros. So essentially, we want to add 2 zeros to the end of this number, since our decimal is right here. So when we do that, we get 78,300 centimeters. Okay, so that 78,300 centimeters is the same or equal to 783 meters. Okay. All right, we're going to do 2 more examples. So we're going to be given a value with a prefix and convert to our base unit in this first one. And again, we can do it by multiplying or dividing by a multiple of 10. So it's the same process. We're going to start with our given. So what is 426 milliliters in liters? So our given there is 426 milliliters. We're going to put that in the top left corner. We want to get to liters. So first we're going to copy down the unit, ml, milliliters, to the bottom because we want it to cancel. We're going to put liters on the top because it's what we want. Then we're going to think about the relationship between the two on the right side. So thinking about our chart, is the base unit liters bigger or is milliliters bigger? Milli. So our base unit is bigger. In this case, milli is 1/1000th. So since milliliters are smaller, we want to think about how many of those it takes to make a liter. Since milli means 1/1000th, it's going to take 1,000 of them to make a liter. Again, we want to do our math. So multiply on the top, divide on the bottom. So 426 times 1 divided by 1,000. Again, we can think about, since we got 3 zeros there, we want to move our decimal place 3 places to the left. So 1, 2, 3. So we should get 0.426 liters, and our milliliters will cancel, top and bottom. Okay, so going from a prefix to a base unit or base unit to prefix, it's the same process. We just have to think about really how that relationship works on the right side. Which one's bigger? How many of the other unit do we need to make it? Now, the last example we're going to do is how do we convert when both of the units have a prefix? Okay, and this is a little bit different. You can see in my railroad tracks here, this is why we call them railroad track, because you can just keep adding on to them when we need them. It's a little bit longer, we have more space in there. And it's because we don't know, I don't know off the top of my head how many centimeters there are in a kilometer or vice versa. I don't know that. I don't want to memorize too many things. It's too many relationships. I want a few simple things that I can keep kind of in my toolbox and pull from when I need them. So what I do know how to go from kilometers to meters. I'm going to put M up here for meter. Okay, so I know how to go from here to here. I also know how to go from meters to centimeters. Notice that both the terms have meter in them. That's our base unit. So I know how to go between my base unit and something with a prefix. So this is like the path we're going to take. So when two things have a prefix, we're going to go to the base unit first, the meter, then we're going to go to the other unit. All right, so let's look at how that works out in our calculation here. So we have 1.3 kilometers and we want to find centimeters. So again, we're going to put our given amount, 1.3 km for kilometers or kilometers, on the top left corner. We're going to copy the kilometers to the bottom because we want them to cancel. Now, since we've got prefixes on both, we're going to go to the base unit first. They have meters in common. That's our base unit. So we're going to put M on the top. Okay. So now we're going to focus in on just the center section. Meters and kilometers. Which one's bigger? So hopefully by now you're seeing that kilo is our biggest one. That's going to get the one next to it. And kilo represents 1,000 times bigger than something, so it's going to take 1,000 meters to make that kilometer. So now, but we're not going to do any math yet. We're just setting things up. But we can see that our kilometers would cancel out. So it kind of helps us ignore them if we go ahead and cross them out. So now, if we were to just look at this next part, we've got meters on the top. We still want to copy them to the bottom. We want those to go away. And what we want in the end is centimeters. So now we're going to go from that base unit to our unit with a prefix centi. So now we want to focus in on that right side all by itself. Doesn't matter what was written before. Centimeters and meters. Which one's bigger? Hopefully you're starting to see that meters are bigger, and it takes 100 centimeters to make a meter. Okay, again, we can cancel out our units. We can get rid of those meters, and it allows us to just have our units that are left over, centimeters. So now we want to do our math. So we're going to multiply across the top, divide by each number on the bottom. So again, they're ones on the bottom, so really that's not going to change our value, but we are going to multiply. So 1.3 times 1,000, so that moves our decimal to the right 3 times. And then we're multiplying by 100, so that moves our decimal 2 more times to the right. So we're moving our decimal 5 places to the right. We should end up with 130,000 centimeters. Okay, so anytime you're seeing something that both the units have prefixes on them, but they've got that base unit in common, we're going to go to that base unit first, because that's what we know how to do, and then we're going to go from the base unit to the other unit we want. Okay, it just kind of breaks up the question a little bit into chunks. That makes it a little bit easier. So hopefully in this metric system PowerPoint, you were able to see that the metric system uses base units to indicate the type of measurement. So liters indicate volume, or grams indicate mass. We are using prefixes. They're used to determine the size of the measurement, so how small it is or how big it is. So kilo is very big, milli is very small. And combining these, we can express many measurements and eliminate the use of extra zeros. We can convert between these units using what we call dimensional analysis. So what we saw with the railroad tracks, that's a fancy name. Railroad tracks is really called dimensional analysis because we're analyzing the dimensions or measurements in our units. All right, thanks guys.